Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1883, minimize the maximum value of two arrays. This problem challenges us to distribute integers across two arrays while minimizing the maximum value in either array. Stay tuned as we break this down step by step and uncover the optimal solution. In this problem, we are tasked with constructing two arrays, ARR1 and ARR2, under specific conditions. The first array, ARR1, must contain exactly unique CNT1 distinct positive integers, all of which are divisible by divisor 1. Similarly, the second array, ARR2, must contain exactly unique CNT2 distinct positive integers, all of which are divisible by divisor 2. Importantly, the two arrays cannot share any common elements. Our goal is to minimize the maximum value among all integers in both arrays combined. For example, if the largest element in ARR1 is 10 and the largest element in ARR2 is 15, then the result would be 15. The challenge is to determine the smallest possible value of this maximum number while meeting all the constraints. Let's consider an example to clarify. Suppose divisor 1 is 2, divisor 2 is 7, unique CNT1 is 3, and unique CNT2 is 2. We need three distinct integers divisible by 2 for ARR1, such as 2, 4, 6, and two distinct integers divisible by 7 for ARR2, such as 7, 14. The largest number in ARR1 is 6, and the largest number in ARR2 is 14. Since we are minimizing the maximum value between the two arrays, the result is 14. Now, for another example, let's take divisor 1 as 4, divisor 2 as 6, unique CNT1 is 4, and unique CNT2 is 3. We can construct ARR1 as 4, 8, 12, 16, and ARR2 as 6, 18, 24. The largest number in ARR1 is 16, and the largest number in ARR2 is 24, so the result is 24. Here's another example to reinforce the concept. If divisor 1 is 3, divisor 2 is 5, unique CNT1 is 2, and unique CNT2 is 3, we need two integers divisible by 3 for ARR1, such as 3, 6, and three integers divisible by 5 for ARR2, such as 5, 10, 15. The largest integer in ARR1 is 6, and the largest integer in ARR2 is 15. Therefore, the result is 15. The constraints for the problem are worth noting here. Both divisors will be at least 2 and can go up to 100,000, while the counts of unique integers needed can be as large as 1 billion. Additionally, the test cases are guaranteed to be feasible, meaning it's always possible to form the arrays under the given constraints. One edge case to keep in mind is when divisor 1 and divisor 2 are relatively prime, ensuring the arrays never overlap. When divisor 1 and divisor 2 share common multiples, special care must be taken to ensure that the arrays do not contain overlapping elements. Additionally, handling very large values of unique CNT1 or unique CNT2 efficiently is critical, as brute force methods would be computationally infeasible for such cases. Correctness is another key challenge, especially when one array requires significantly more distinct integers than the other. The core insight to solving this problem lies in finding the smallest integers divisible by divisor 1 and divisor 2 while ensuring no overlap between the two arrays. Optimizations are essential to handle the large constraints effectively, which means leveraging mathematical properties of divisors and efficient algorithms to construct the arrays. To tackle problem number 1883, our goal is to minimize the maximum integer value across two arrays, ARR1 and ARR2, while meeting specific constraints. These constraints involve ensuring unique integers in each array, where the integers must be divisible by given divisors, and the arrays must satisfy certain count requirements. One straightforward way to approach this is through brute force. The brute force method involves iterating through all possible maximum values, starting from 1, and checking if we can construct the arrays for each candidate maximum value. For any given maximum value x, we determine the numbers that are divisible by divisor 1 for ARR1 and those divisible by divisor 2 for ARR2. A crucial step is ensuring that these arrays remain distinct, meaning no overlap between the two. While this approach is intuitive, its major drawback is its inefficiency. For larger constraints, the sheer number of iterations and the need to generate numbers repeatedly for each candidate make this method computationally prohibitive. It's clear that we need a more optimized approach to solve the problem within reasonable time limits. Now, let's consider an optimized approach using binary search to minimize the maximum value. The key insight here is that this problem exhibits a property of monotonicity, which means if a certain maximum value x satisfies the constraints, then all values greater than x will also satisfy them. This allows us to narrow down the solution space efficiently. Instead of iterating through all possible maximum values, we use binary search on the range of possible values for x. For any candidate maximum value, we calculate the number of integers divisible by divisor 1 within the range, 1x, which corresponds to the potential elements of ARR1. Similarly, we calculate the integers divisible by divisor 2 for ARR2. To ensure distinct arrays, we account for overlap by using the least common multiple, LCM, of the two divisors, which helps us exclude duplicates. After determining these counts, we check if they meet the required unique CNT1 and unique CNT2. If they do, we adjust the search range to explore smaller maximum values. If not, we shift the range to explore larger values. The aha moment here is recognizing that binary search, combined with efficient computation of divisible counts, avoids the need to generate arrays explicitly and drastically reduces computational effort. The binary search approach is not only conceptually sound but also highly efficient in practice. By performing binary search on the range, 1, max_value, we limit the number of iterations to O, log, max_value. Within each iteration, computing the counts of divisible numbers and handling overlaps through the LCM is an O(1) operation. This makes the overall complexity of the approach O, log, max_value, which is a significant improvement over brute force. Given the problem's constraints, with max_value reaching as high as 10 to the power of 9, this optimization is essential. The chosen strategy leverages the binary search method because it balances efficiency with ease of implementation, relying on mathematical properties like divisors and the LCM to simplify the calculations. When compared to brute force, this approach eliminates the overhead of array generation and the exponential growth of iterations. While it requires a clear understanding of divisor relationships, the trade-offs are minimal, making it the most practical and scalable solution for this problem. Ultimately, the binary search approach enables us to solve the problem efficiently, even under the most challenging constraints. In this problem, we aim to minimize the maximum value in two arrays, ARR1 and ARR2, while meeting certain constraints. Each array must contain a specified number of unique integers, denoted by unique CNT1 and unique CNT2. Additionally, these integers must adhere to divisibility rules defined by div1 and div2. The integers are drawn from the positive integers starting at 1. To solve this, we can frame the problem as finding the smallest possible maximum integer x that allows us to satisfy these constraints. Binary search is a natural choice here because we can efficiently test different values of x within the range, 1, 10 to the power of 9. To begin the binary search, we initialize low to 1 and high to 10 to the power of 9. A helper function, canDistribute x, will help us determine if it's feasible to meet the constraints with integers drawn from 1, x. The helper function canDistribute x is key to this approach. First, we calculate how many integers in the range, 1x, are divisible by div1, div2, and their least common multiple, or LCM. These counts are stored as countDiv1, countDiv2, and countBoth. From these, we determine the number of unique integers available for each array while accounting for overlaps. Unique 1 represents integers divisible by div1 but not shared with div2, and unique 2 represents integers divisible by div2 but not shared with div1. The shared integers, divisible by both div1 and div2, are also calculated. To meet the constraints, we need unique CNT1 integers for ARR1 and unique CNT2 integers for ARR2. If there are gaps, shared integers can fill those requirements. If the constraints are satisfied for the given x, the function returns true. Based on this, the binary search range is updated. If canDistribute, mid, is true, we set high to mid, aiming to minimize x. Otherwise, we increase low to mid plus 1, as the current x is insufficient. The binary search process continues until low equals high. At this point, low represents the smallest maximum value that satisfies the constraints for both arrays. This value is then returned as the result, giving us the minimized maximum value. The algorithm relies on several insights to achieve efficiency. By using binary search on the maximum value, we avoid the need to iterate through all possible values. The use of mathematical properties like divisibility and least common multiples ensures that we allocate integers correctly while avoiding unnecessary overlap. Finally, the shared integers, those divisible by both div1 and div2, play a critical role in balancing the allocation between the two arrays, making it possible to meet both constraints even when other integers are insufficient. The algorithm is straightforward in terms of data structures, as it relies solely on integers and arithmetic operations. Binary search efficiently narrows down the range, 1, 10 to the power of 9, reducing the complexity of the problem. Each iteration of the helper function involves calculating divisors and least common multiples, which is done in logarithmic time relative to the smaller divisor. The overall time complexity is therefore O log, max value, log, min, div1, div2. This ensures the algorithm scales well even for large inputs. Several edge cases must also be considered. If the total number of required integers exceeds the range of x, the function must return false. When div1 and div2 are coprime, there are no shared integers, which the algorithm must handle appropriately. Additionally, the algorithm must be robust against extreme values near the input limits, ensuring correctness and efficiency even in such scenarios. To better understand the solution, let's consider an example. Suppose div1 is 2, div2 is 3, uniquecnt1 is 4, and uniquecnt2 is 6. The output in this case is 10. This means that using integers in the range 1, 10, we can allocate 4 integers divisible by 2 to ARR1 and 6 integers divisible by 3 to ARR2. The key is that the maximum value, 10, is minimized while meeting all constraints. This demonstrates how the algorithm balances the requirements for both arrays and efficiently finds the smallest possible maximum value that satisfies the problem's conditions. Here, we begin the Python implementation of the problem. First, we define the minimizeSet function inside the solution class, which takes 4 inputs, divisor1, divisor2, uniquecnt1, and uniquecnt2. These inputs represent the two divisors and the desired counts of unique integers not divisible by these divisors. To help us calculate the count of numbers that are not divisible by either divisor, we define a helper function count_non_divisible. This function uses the floor division operator to calculate how many numbers up to a given value m are divisible by divisor 1, divisor 2, and their least common multiple. By subtracting these counts from m, we obtain the desired count of non-divisible numbers. Additionally, we define another helper function LCM to compute the least common multiple of two integers using their greatest common divisor, which is imported from Python's math module. Now, we initialize our binary search range with left set to 1 and right set to a very large value, 10*10. The binary search loop begins, where we calculate the midpoint mid and determine if it's possible to select the required numbers under the given constraints. We calculate non_div to check the total count of numbers not divisible by both divisors, and also compute non_div1 and non_div2 to ensure that the counts for each unique group are sufficient. If the conditions are satisfied, we adjust our search range by setting right to mid, attempting to minimize the maximum value further. On the other hand, if the conditions are not satisfied for the current midpoint, we modify the search range by setting left to mid +1. This narrows the range toward larger values of mid in our binary search. Once the loop terminates, the left pointer will represent the smallest possible maximum value that satisfies all the constraints, and we return it as the result. This binary search approach ensures that we efficiently find the minimum maximum value while adhering to the problem's requirements. Here, we begin by importing the necessary utilities, including biginteger, to handle large numbers during calculations. The primary method, minimizeSet, is designed to find the smallest maximum value of two arrays under the given constraints. To achieve this, we define a helper function, LCM, to calculate the least common multiple of two numbers using their greatest common divisor. This is crucial for determining overlaps in the numbers divisible by either divisor. Next, we implement another helper function, count_non_divisible, which computes how many numbers up to a given limit, m, are not divisible by either divisor 1 or divisor 2. It does this by subtracting the count of numbers divisible by each divisor and their least common multiple from the total numbers. With these helpers in place, we initialize a binary search range between 1 and 10 to the power of 10, setting up the framework to find the minimum possible maximum value efficiently. The while loop begins this search by calculating the midpoint of the current range, mid, and using count non-divisible to determine how many numbers within this range satisfy the divisibility constraints. Next, we evaluate whether the current mid value can satisfy the requirements for the two arrays. Specifically, we check if the total count of non-divisible numbers, non-DID, is at least the sum of unique CNT1 and unique CNT2. Additionally, we ensure that there are enough numbers not divisible by divisor 1 for the first array, and enough not divisible by divisor 2 for the second array. If these conditions are met, it means the current mid value is a valid candidate, so we narrow the search range by setting right to mid, aiming to find a smaller maximum. Otherwise, we adjust the left boundary to mid plus 1, expanding the range to search for a higher mid value that satisfies the constraints. Once the loop concludes, left will point to the smallest maximum value that fulfills all the requirements. Finally, we return this value as an integer, completing the implementation of the solution. In this example, we are tasked with finding the smallest integer m that satisfies three specific conditions. First, there must be at least 5 numbers less than or equal to m that are not divisible by either 2 or 3. These 5 numbers come from the sum of unique CNT1, which is 2, and unique CNT2, which is 3. Second, we require at least 2 numbers less than or equal to m that are not divisible by 2. Finally, there must be at least 3 numbers less than or equal to m that are not divisible by 3. To solve this problem efficiently, we use binary search. We initialize the search range with left set to 1 and right set to 10 billion, aiming to narrow down the range to find the minimum m that satisfies all these conditions. To begin, we calculate the midpoint of the range, mid, as the average of left and right, which is initially 5 billion. We then compute the least common multiple, LCM, of 2 and 3, which is 6. Using this, we determine the count of numbers less than or equal to mid that are divisible by 2, by 3, and by both 2 and 3. Subtracting these counts from mid gives us the count of numbers not divisible by either divisor. For the first iteration, this value is 1.67 billion, which meets the condition of at least 5 numbers. Separately, we calculate the counts of numbers not divisible by only 2 or by only 3, and these also meet their respective thresholds. Since all conditions are satisfied, we update right to the current mid and repeat the process with a smaller range. The same steps are followed in subsequent iterations, continually having mid and refining the range until left equals right. After a series of iterations, we find that the smallest value of m that meets all the conditions is 5. This means that when m is 5, there are at least 5 numbers that are not divisible by 2 or 3, at least 2 numbers not divisible by 2, and at least 3 numbers not divisible by 3. With this result in hand, we move to a new example where the divisors and counts are different. In this second example, divisor 1 is 4, divisor 2 is 6, unique CNT1 is 5, and unique CNT2 is 7. The combined requirement for numbers not divisible by either divisor is now 12. We follow the same binary search approach, initializing left as 1 and right as 10 billion to find the smallest m that satisfies these conditions. Using the binary search method outlined earlier, we compute intermediate values such as the LCM of 4 and 6, which is 12, and the counts of numbers not divisible by either divisor. The approach involves repeatedly narrowing the range by updating left or right based on whether the midpoint satisfies the conditions. In this example, we ensure there are at least 12 numbers not divisible by either 4 or 6, at least 5 numbers not divisible by 4, and at least 7 numbers not divisible by 6. Through successive iterations, we eventually determine that the smallest m satisfying all conditions is 25. This demonstrates how the binary search efficiently hones in on the solution by leveraging these intermediate calculations. In the third example, divisor 1 is 7, divisor 2 is 9, unique CNT1 is 10, and unique CNT2 is 15. This means we need at least 25 numbers not divisible by either 7 or 9, at least 10 numbers not divisible by 7, and at least 15 numbers not divisible by 9. We calculate the LCM of 7 and 9, which is 63, and use binary search to find the smallest m that meets these requirements. As before, we compute intermediate values for each iteration, adjusting the range until left equals right, and ultimately find that the smallest m is 63. This consistent application of binary search highlights its power in solving problems that involve minimizing values under specific constraints. To analyze the time complexity of our solution, we begin with the binary search component. Binary search operates over the range from 1 to 10 to the power of 10, and the number of iterations it requires depends on the logarithm of this range. Specifically, it performs log 10 to the power of 10 iterations, which is equivalent to log 2 to the power of 33, approximately 33 iterations in the worst case. This means the binary search contributes a constant number of iterations in practice. Next, we consider the count_non_divisible function, which is called during each binary search step. This function determines how many numbers up to a given value mid are not divisible by either divisor 1 or divisor 2. To achieve this, it performs a series of operations, calculating m/divisor 1, m/divisor 2, and the least common multiple of the two divisors. The LCM calculation involves finding the greatest common divisor using the Euclidean algorithm, which runs in log min divisor 1 divisor 2. Therefore, the count_non_divisible function has a time complexity of log min divisor 1 divisor 2. Now, focusing more on the LCM calculation, it relies on the GCD computation. The Euclidean algorithm used to compute the GCD takes log min divisor 1 divisor 2 steps. Once the GCD is determined, the LCM can be calculated in constant time through simple arithmetic. Consequently, the time complexity for each binary search iteration is log min divisor 1 divisor 2. Since binary search itself performs log 10 to the power of 10 iterations, the total time complexity of the solution becomes log 10 to the power of 10 log min divisor 1 divisor 2. In extreme cases, such as when divisor 1 and divisor 2 are very large, close to 10 to the power of 9, the logarithmic term log min divisor 1 divisor 2 approaches log 10 to the power of 9, which is approximately 30. Combining this with the 33 iterations from binary search, the worst-case time complexity overall is roughly 1000. Now let's discuss the space complexity of the solution. The primary contributor to space usage is the recursive stack used by the GCD function. The Euclidean algorithm, which is used to calculate the GCD, has a recursive depth of log min divisor 1 divisor 2. Since this depth grows logarithmically, it remains quite small in practice. Apart from this, the solution uses a constant number of auxiliary variables such as left, right, mid, and a few others for arithmetic operations, all of which require only one space. As a result, the overall space complexity of the solution is log min divisor 1 divisor 2 due to the GCD recursion, which is efficient in minimal. When comparing the optimized approach to a naive one, the difference in efficiency becomes clear. A naive approach would involve iterating through all integers up to the maximum value, checking the divisibility conditions for each number. This would result in a time complexity of n, where n is as large as 10 to the power of 10. Such a method is computationally infeasible for large inputs due to the sheer number of iterations. On the other hand, the optimized approach combines binary search with efficient divisibility counting using LCM and GCD. This drastically reduces the search space and achieves a time complexity of log 10 to the power of 10 log min divisor 1 divisor 2. This optimization demonstrates how leveraging mathematical insights can transform an otherwise impractical problem into one that is computationally efficient. Finally, let's analyze the algorithm under best, average, and worst-case scenarios. In the best case, where the required uniquecnt1 and uniquecnt2 are very small, the binary search converges rapidly, requiring fewer iterations. Even here, the time complexity remains within log 10 to the power of 10 log min divisor 1 divisor 2. For typical or average inputs, the binary search performs its usual 33 iterations, and the divisibility checks involve logarithmic operations consistent with the derived complexity. In the worst case, when divisor 1 and divisor 2 are extremely large, close to 10 to the power of 9, the GCD computation takes the maximum possible time. This makes the time complexity log 10 to the power of 10 log 10 to the power of 9, which is still highly efficient compared to a naive approach. To summarize, the binary search reduces the search range logarithmically while the divisibility check relies on fast GCD computations, making the overall complexity a product of these logarithmic terms. This efficiency highlights the power of the optimized approach over brute force methods. When tackling this problem, there are a few common pitfalls to watch out for. First, it's crucial to consider the constraints on the arrays. If you overlook the limits on the size of ARR1 and ARR2, you might end up writing a solution that exceeds time or space constraints. Always take a moment to analyze these limits before diving into implementation. Another mistake is relying on brute force approaches. For small inputs, brute forcing all combinations might seem feasible, but as the input size grows, this approach quickly becomes impractical due to its exponential time complexity. This will almost certainly result in time limit exceeded errors. Additionally, you need to be mindful of duplicates. When distributing integers between ARR1 and ARR2, ensuring that each integer is unique across the two arrays is critical. Failing to do so can lead to invalid solutions. Lastly, don't overlook edge cases. Scenarios like n equals 1, arrays with extreme values, or arrays where all elements are the same can often break your solution. Make sure to test your implementation on a variety of edge cases to ensure its robustness. Binary search is a common approach to solving this problem, but it requires careful handling of the bounds. Mismanaging the binary search bounds, such as improperly setting the midpoint or failing to update them correctly, can lead to infinite loops or incorrect results. Pay special attention to debugging boundary conditions to avoid these issues. Now, from an interview perspective, this problem is a great example of an optimization problem involving constraints. Recognizing this pattern can guide your approach early on. Problems like this are often solved using binary search on the answer space, where you test possible maximum values iteratively. Familiarizing yourself with this technique can be a game changer in interviews, as it appears frequently in optimization problems. Finally, remember that solving this problem is about balancing trade-offs. While binary search is efficient, it demands precision in implementation. Be mindful of off-by-one errors and other logical pitfalls that can derail your solution. This problem is closely related to several others that involve minimizing or balancing maximum values under constraints. For example, LeetCode number 410, split array largest sum, asks you to minimize the largest sum among k subarrays. Similarly, LeetCode number 875, Cocoa eating bananas, requires you to minimize the maximum eating speed. Other related problems include LeetCode number 1231, divide chocolate, and LeetCode number 1011, capacity to ship packages within D days, which both involve distributing resources to minimize a maximum value. Exploring these problems can help you build a strong foundation for tackling similar optimization challenges. As for alternative approaches, one popular method is binary search on the answer space. Here, you test possible maximum values for the arrays and check if the distribution is valid. This approach is efficient, with a time complexity of n*log, max_val, but it does require careful implementation of the validity check. Another option is using greedy algorithms, which iteratively distribute integers between the arrays in a way that minimizes the maximum value. While these are easier to implement, they may not always yield the optimal solution, especially for complex input distributions. Dynamic programming is another approach to solving this problem. By using a DP table, you can systematically explore all possible distributions of integers between the arrays and determine the configuration that minimizes the maximum value. This method guarantees an optimal solution, but it comes with a significant trade-off in terms of computational expense. Depending on the implementation, the time complexity can be n² or higher, making it less practical for larger input sizes. While dynamic programming provides a comprehensive way to solve the problem, it's often reserved for cases where efficiency is less critical or when other approaches, like binary search or greedy algorithms, fail to work. Choosing the right approach ultimately depends on the specific constraints and requirements of the problem you're solving. Thank you for following along. We explored how to solve LeetCode problem number 1883 by optimizing the distribution of integers between two arrays. Remember, problems like this are excellent for sharpening your optimization skills. Don't forget to like and subscribe for more coding walkthroughs. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!